In this paper, we introduce a single domain generalization method for LiDAR semantic segmentation or DGLSS. We aim to ensure good performance not only in the source domain, but also in the unseen domain while training with only one source domain. We also focus on learning from a denser source domain, as using sparser LiDAR data in an application is much more efficient and a more likely scenario. We mainly focus on domain gaps from different sparsity and scene distributions and propose two constraints to learn generalizable representations. And by utilizing those two constraints in our framework, we achieved improved performance in the unseen domain and source domain in the proposed standardized training and evaluation setting compared to other baselines. The problem with existing LiDAR semantic segmentation models is that they often fail in real-world unseen target domain data with domain gaps. This is why we propose a single domain generalization method for LiDAR semantic segmentation. This figure is the most basic pipeline of a semantic segmentation model that uses a single source domain. The input point cloud is voxelized, and the adopted base model Minkowski-net outputs voxel-wise class predictions while trained with weighted cross-entropy loss. But learning a model robust to domain gaps with a single source domain makes it difficult to learn domain invariant features. Therefore, the first step is to augment an additional domain to enhance generalizability. To achieve high performance in unseen domains with unknown sparsity, we augment domains with diverse sparsity. LiDAR scan lines are randomly dropped to simulate the local structures of real LiDAR data. Now we can make a framework that utilizes both the source domain and augmented domain. Point clouds from both domains are voxelized and fed to the shared semantic segmentation model, but we still need additional constraints because this framework cannot ensure the process of learning sparsity invariant features. Next is step 2, where we propose the sparsity invariant feature consistency SIFC to learn sparsity invariant features. Since the source domain and augmented domain data depict the same scene but only different in sparsity, the voxels in the same location should have identical features. So the goal is to enforce the consistency in encoded sparse features regardless of the domain. But not all voxels in the source domain have corresponding voxels in the augmented domain. Therefore, we handle the voxels that have a corresponding pair in the other domain and those that do not in a different manner. If the source domain voxel has a corresponding voxel pair in the augmented domain, we use L1 loss to maintain the features of the corresponding voxels to be similar. Next, we deal with voxels with no corresponding pairs by making a virtual voxel in the augmented domain. We select the k nearest voxel features and aggregate them using weighted sum. However, aggregating all k neighboring features can have a negative effect in the learning process due to the propagation of irrelevant class features. Therefore, we further filter out neighboring features by calculating feature affinity between the source voxel features. Then the corresponding augmented voxels that have higher affinity than the predefined threshold are aggregated. Finally, this aggregated voxel feature is used to supervise the source domain voxel with L1 loss. The final SIFC loss is formulated as the summation of case 1 and case 2. But even with SIFC, we still need an additional constraint to deal with scene difference domain gaps. In step 3, we propose the semantic correlation consistency SCC to deal with scene distribution differences. SCC aims to maintain relationships between classes that are consistent throughout domains, such as that cars are located on top of roads. Both the source and augmented domain encoded sparse features are decoded, fed to the metric learner, and where the SCC loss is applied to the constructed embedding space. To impose SCC, say that we have a single batch of embedding space features from both source and augmented domain scans. For each scan in the batch, we obtain class specific prototypes by taking the mean of the features with same labels and construct a prototype matrix CEI. In that way, we can make prototype matrices for each scan. Then we multiply the transpose of the prototype matrix to itself and obtain the prototype correlation matrix. We then impose the SCC loss to supervise the correlation matrices to be same regardless of the scene, which helps the model learn scene invariant features. Now we can build the final framework as shown in this figure. We first augment the new domain with different sparsity and apply SIFC to obtain sparsity invariant encoded voxel features. Then finally, SCC is used to enforce class correlation consistency throughout all scenes. For the experiments, we propose a standardized training and evaluation setting, as such setting for domain generalization has been absent. We employ 4 real-world LiDAR datasets and carefully select 10 common classes that overlap among most datasets. Then we map the labels of each dataset to the common labels. These are the quantitative results. We implement baseline methods using general-purpose DG methods applicable to point clouds. The left side table shows the results of our method and baselines trained on Semantic and Waymo. Our method successfully shows improvement over the base method and even LiDAR domain adaptation methods. We also conducted ablation studies as shown in the right side table. Using an augmented domain increases the overall segmentation performance for all datasets. When adding SIFC, large objects such as cars and trucks benefit mostly, and adding SCC further increases the mean IOU in unseen target domains, showing the strength of the proposed constraints. These are the qualitative results when trained with source dataset Semantic and tested on target domain using LiDAR-Seg. Compared to the baselines, our method can correctly segment the points in the scene. These are additional qualitative results. To sum up, the proposed method is the first domain generalization approach that primarily aims at LiDAR semantic segmentation using only a single source domain. Also, constraining the model with SIFC and SCC aided the model to generalize in unseen domains. And finally, using the proposed standardized training and evaluation setting, the proposed method achieved improved performance in the unseen domains and source domain compared to other baselines. This is the end of our presentation. Thank you for listening.